Have you ever wondered why some electronic circuits seem to perform their best at a very specific frequency, almost as if they have a favorite tune to play? This remarkable characteristic, vital in everything from radio receivers to medical imaging, is deeply connected to a circuit's ability to store and releases energy efficiently. Understanding this behavior is key to designing high-performance systems. The quality factor, or Q factor, in alternating current circuits is a dimensionless parameter that quantifies a circuit's selectivity and its energy storage capability relative to its energy dissipation. In simpler terms, it tells us how good a resonant circuit is at distinguishing between the desired resonant frequency and other frequencies, making it sharper and more efficient. A higher Q factor indicates less energy loss and a more sharply defined resonant peak. The why behind the Q factor lies in the balance between a circuit's reactive components, like inductors and capacitors, which store energy, and its resistive components, which dissipate energy as heat. At resonance, the energy oscillates between the inductor's magnetic field and the capacitor's electric field. The Q factor is essentially a ratio, the maximum energy stored in these reactive elements divided by the energy lost per cycle in the resistance. Factors that influence Q include the inherent resistance of the inductor's wire, the dielectric losses in the capacitor, and any external load resistance. Reducing these losses directly increases the Q factor. To practically assess or design for a specific Q factor, you need to consider the resonant frequency, the inductance, capacitance, and total resistance. For a series RLC circuit, Q is calculated as the inductive or capacitive reactance at resonance divided by the total resistance. A higher inductance or capacitance relative to resistance will yield a higher Q. In practical applications, engineers often select components with very low equivalent series, resistance for inductors and low dissipation factors for capacitors to achieve high Q designs for filters, oscillators, and tuned amplifiers. An interesting insider detail is the relationship between the Q factor and the bandwidth of a resonant circuit. Bandwidth is the range of frequencies over which the circuit's response is considered effective. A higher Q factor means a narrower bandwidth, indicating superior frequency selectivity. This is crucial for applications like tuning into a single radio station without interference from adjacent channels. Conversely, a lower Q factor results in a wider bandwidth, useful when you need to pass a broader range of frequencies. Ultimately, grasping the quality factor empowers you to understand and manipulate the frequency response of alternating current circuits. By appreciating the interplay between energy storage and energy dissipation, you can design circuits that are either highly selective for precise frequency tuning or broadband for wider signal processing, ensuring optimal performance and efficiency in countless electronic applications.